Okay, so we've kind of talked about what a scheduler is, and we've talked about the goals of a scheduler. And now what I'd like to do is I'd like to talk about a couple of different scheduling algorithms. So the first kind of scheduling algorithm is called first come, first serve. And it's something that you would see if you were on a large computer system that processed jobs. Okay, so this is really common in a batch computer system that processes jobs. So jobs are processes that have to run. So an example of this might be like compute a grade report, or maybe compute credit card bill, or process emails on an email server. Okay, so if I were to draw a diagram of what the scheduling algorithm would look like for first come, first serve, it would look something like this. We have the running state. So a process can get moved to the running state, can exit. We can do I/O or synchronization, in which case we're blocked until that completes. And we also have a ready state. And the ready state passes processes from the ready state to the running state. And when we create a process, I'm going to just move this up a little bit more. When a create happens, the create adds the process that's just been created to the back of a queue. So the ready state consists of a list of processes, P0, P1, down to Pn. And these are processes that are in the queue. So this is the front of the queue, and this is the back of the queue. So when you create a new process, it's going to go to the back of the queue. When a process is no longer blocked, it is also going to go to the back of the queue. And what the scheduler is going to do is every time there's a process leaves the running state, either because it exits or because it's doing I/O, we're going to go back to the ready state and we're going to select the process that's at the front of the queue. So in this example, some process is done running, we're going to select P0 and remove that from the front of the queue. And then we're going to move P0 over here and let P0 run. P0 is going to run and run and run and run and run as long as it needs to run. And if it starts doing I/O, we'll pull it off of the running queue and we'll move it over into the blocked state. And then we're going to go and grab P1, the next process in the ready queue, and then we'll put P1 over here and start it running. And we'll let it run for as long as it needs to run until it's done running. Either it exits because it's completed or it does some IO. And we just sort of repeat that process. Now, when P0 is done being in the block state, we're going to move it from the block state to the bottom of the queue. So it gets back in line and waits its turn to run. All right, so that's the idea of first come, first serve. So in terms of simplicity, the algorithm itself is pretty simple. If you can implement a queue, you can get first come, first serve to work really nicely. So on the one hand, it's simple. On the other hand, though, we have some problems. So I want to show you an example of what I mean. So I'm going to just write down it's problematic and then we'll investigate it. Okay, so we'll slide this over. And what I want to consider is, let's say we have a process A, and here's what process A does. It needs 1 second of CPU, and then it needs 5 milliseconds of IO, all right? And here's a process, and it does this forever. Maybe it's some kind of, let's say it's like a security scanning program. It does a little bit of IO, reads some data in, and then spends a second of CPU processing that data. So it does this infinity times. Okay, it's like a while true. All right, and now let's look at a process B that does something slightly different. Okay, so here's our process B. And what process B does is it uses up a very little bit of CPU, 1 microsecond of CPU, and it does 5 milliseconds of IO. And it does this 1,000 times. Okay, now let's take a look at the way this first come, first serve works. All right, so first come, first serve works because, first come, first serve works. And if you notice, one thing that I did here is there's only an arrow going from ready to running. In the previous example, if we back up a little bit, when we first started talking about the scheduler, we had the ability for a process P0 to go from the running state over to the ready state. So the CPU could, the operating system could pull P0 off, even though if it wanted to keep running, and bring it back to the ready state so that it would take turns with other processes that are running. All right, we're not doing that in our first come, first serve batch computer system. We basically let our process P1, for example, run as long as it wants to run on the CPU. And when it does IO, we'll pull it off, or if it exits, we'll pull it off. But until then, it's going to run forever. So the problem we have here is that PA is kind of selfish. It's going to run for 1 second of CPU, even though PV just needs to run for a short period of time before it does its IO. Unfortunately, PV is going to have to wait for PA to finish running its 1 second of CPU. So the question is, how long will it take for PV to finish without preemption? Okay, or context switching. Okay, if we don't allow preemption or context switching, how long is it going to take for PV to run? Good question. So let's see if we can chart this out a little bit and develop an understanding of how long it's going to take to run. You might say, oh, well, PV is going to be able to run, well, let's see, it's 1 microsecond plus 5 milliseconds. times 1,000. That's how much time it runs. Maybe that's the answer, okay? Because we have to do this 1 microsecond of CPU time and 5 milliseconds of IO time. We have to do that 1,000 times. So if we add all this up together, what we're going to get is 1,000 times 1 microsecond. We'll just do the math out here. So that's 1,000 times 10 to the minus 6. That's a microsecond, plus 1,000 times 5 times 10 to the minus 3. Okay, so that's 10 to the minus 3 plus 5,000 times 10 to the minus 3. So that's 5,001 times 10 to the minus 3. So that's how many seconds. That's how many seconds we have to work with. A millisecond is 1,000th of a second, and a microsecond is 1 millionth of a second. So that's how I got those numbers. So you might think that that's the answer, but it's actually not. It would be the answer. This would be the answer if PB was able to run by itself without any interference from PA. But unfortunately, PB and PA have to share the CPU. And when that happens, we have something that looks a little bit, we can sort of draw a diagram that shows, we can show the pattern of PA running. So PA wants to run for 1 second, and then it has a brief period of time. This isn't exactly to scale, but it has 5 milliseconds of IO. So this is CPU, and then this is IO. Okay. So during the time that PA is running on the CPU, PB is not allowed to run. When the IO, the 5 milliseconds of IO happens, the operating system using first come, first serve will go back to the ready queue and say, is anybody able to run? And at that point, PB will say, yeah, I can run. So we'll let PB run. So PB run's going to run briefly for 1 microsecond. Let's zoom in here. I seem to be writing very tiny here. So 1 microsecond. And then PB is going to have its own 5 milliseconds of CPU. And by the time PB's 5 milliseconds of CPU ends, unfortunately, we're going to be in a situation where PA is running again. So what's going to happen is PB is going to have to wait. So here it's just waiting. It's just it's on the ready queue. And as soon as that 1 second ends and we do I'm going to just move this down a little bit because we're getting a little cramped for space. Okay, as soon as PA is done running and goes into its 5 milliseconds of IO, again, then we'll allow PB to run on the CPU for 1 microsecond. And then it can do its IO for 5 milliseconds. And this process repeats again over and over and over again. So if we look at what's going to happen effectively, let me undo that. So effectively, what's going to happen is that we're going to have PB following this pattern here of 1 microsecond of running, 5 milliseconds of IO, and then a whole bunch of time on the ready queue. In fact, it's basically about 1 second on the ready queue. All right. So if we're trying to answer the question, we can actually compute exactly what it is. It's 1 second minus 1 microsecond on the ready queue. Okay, so if we're going to compute, then how much time it takes PB to actually run. If PB is sharing the CPU with PA, we're going to end up in this pattern where there's a whole bunch of time that PB is on the ready queue and it's not doing anything. It's basically idle. All right, and so it's actually going to be 1,000 times 1 microsecond plus 1 second minus 1 microsecond plus 5 milliseconds. All right, so if we do a little bit of simplifying math, we're really talking about 1,000 times the time that PA is running, basically. So that's 1,000 seconds times 1,000 seconds plus 5,000 times 10 to the minus 3 seconds, and that's going to give us 1,005 seconds. So that's effectively that's the response time for PB to complete. Okay, so that kind of sucks, actually. And it's because of the problem that PA is occupying the CPU, and until PA is finished using the CPU, PB will not be allowed to run. And that's because we don't have preemption. All right, so first come, first serve without preemption is not so great. It's really not great. They are sharing, PA and PB are sharing, but we could do a better job of sharing. All right, so let's see if we can improve this. All right, let's say we add preemption. Let's say we add preemption or context switching. All right, so if we do that, what I'd like to say is that we'll say that we're going to make this assumption that every 10 milliseconds we allow a context switch. Okay, so what does that then make the what does that then make this look like? So let's let PA run. So PA is going to run for 10 milliseconds. Then we're going to do a context switch to allow PB to run. So PB will then run for 1 microsecond. And during that time, PA is idle. It is in the ready state. So PB runs for 1 microsecond. And then for 5 milliseconds, it's doing IO. Now, during those 5 milliseconds, PB is going to get a chance to run, or PA is going to get a chance to run again. So it's going to run for 10 milliseconds. And there's going to be a period of idle time while PB waits for PA to finish using its unit of time. And then PA is going to go idle again. PA PB is going to run for 1 microsecond, and then it's going to start doing its 5 milliseconds of I/O. During that 5 milliseconds of I/O, PA is allowed to run, and it will run for 10 milliseconds again. And during the 10 milliseconds, after that 5 milliseconds of I/O, we're going to have PB waiting, idle, until this 10 milliseconds is up, and we're going to repeat that pattern of 1 microsecond, idle for 1 microsecond, and then this is allowed to run again for 10 milliseconds. And we got 5 milliseconds of I/O, and then we're idle in the ready state. Okay, so we're going to repeat that pattern. So if we look at this, effectively what's happening is we've got, this is going to run this chunk here, or maybe I'll just highlight it this way. So this pattern here of 1 microsecond, of 1 microsecond for CPU utilization, 5 milliseconds of I/O, and then whatever this is, and if we look at this, what is this? It's effective. It is basically 5 milliseconds of wait time, right? If we're doing 5 milliseconds of I/O here, that's allowing PA to run for 5 milliseconds. And then when that 5 milliseconds is up, we're just waiting. We're idle and waiting. Okay, so if we total that up, we then have 1 times 10 to the minus 6 plus 10 to the, 10 times 10 to the minus 3. And then if we multiply this by 1,000, because we wanted to run PB 1,000 times, then we have 1,000 times 10 to the minus 6 plus 10,000 times 10 to the minus 3. And then we can just do a little bit of reduction. So 1,000, we'll get it all to 10, we'll just get it all to 10 to the 0. So we'll get it as close as we can, get this into seconds. So 1,000 times 10 to the minus 6 is 1 times 10 to the minus 3 plus 10,000. So we'll get rid of that, and that gets rid of that, and that gives us 10. So if we add those two together, we have 10.123 seconds. So that is the response time for PB with preemption or with context switching. Okay, so that's pretty cool. So if we allow preemption or context switching, we get a much better response time for PB. And that's because we're allowing PA and PB to share the use of the CPU. In the previous example here, we did not allow PA and PB to share the CPU. So the only time that PB was allowed to get access to the CPU was when PA was done with it. All right, and PA had a pattern where it would use it for a second, give it up for 5 milliseconds. Want to use it for a second, give it up for 5 seconds. So the result of that was we had a very large response time for PB. But when PA and PB share the CPU, and the rules are everyone's allowed 10 milliseconds, then you have to give it up. When that happens, we allow PB to run to completion fairly quickly. We got a much better response time, 10 seconds versus 1,000 seconds. So that's pretty cool. So one thing I would say is, yay, context switching. All right, let's take a look at a different strategy for scheduling jobs and see if it makes a difference. So this is a technique called shortest I'm just gonna, this will be in your notes, so I just want to make sure I'm clear on this. We have space to do this? Yeah. Okay. I'm doing you a favor here. Okay. I'm just gonna move this. Whoops. Let's try that again. I just want to do a little bit of structural organization here. Okay. I just want to move this down here. And I'm going to call this scheduling algorithms. Okay, so the first one is first come, first serve. That's kind of annoying. I'll just leave it there. First come, first serve. Okay, so the next one we're going to look at is shortest job first. So this is kind of interesting. All right, so let's say we have a situation where there's a setup to make shortest job first work. So number one, here are the rules. Rule number one, all job times known in advance. Rule number two, all jobs in ready state. Number three, no preemption. Okay, and number four, jobs executed in order from smallest to largest. Okay, so let's take a look at an example. All right, so here's example one. We have some jobs that arrive into the ready queue. All right, so example number one. Jobs arrive into ready queue. But we organize them first come, first serve. So in this case, we're not going to use the idea of shortest job first initially, but we're going to do a comparison, okay? So job A is 10 minutes. Job B is 1 minute. Job C is 4 minutes. And job D is 2 minutes. Okay, so what we're going to do then is we're going to process the jobs in the order that they're received. Okay. So we're going to process the jobs in the order that were received, and then the question we want to answer is, what is the response time? Is the average response time. That's the question. All right, so how do we compute that average response time? Well, let's take the average of the time that it takes for the jobs to complete. So the average of the time that it takes the jobs to complete is the sum of all the times that it takes all the jobs to complete. So, and it's not quite as straightforward as you might think. So the amount of time, since all of these jobs, we're going to say all the jobs A through D arrive simultaneously. So we're going to say arrive simultaneously. So that's actually really important. So I'm going to highlight that in purple. They arrive simultaneously into the queue. Okay, so let's calculate the response time. We're going to do first come, first serve. So A is going to go first. So how much time does it take for A to complete? Total time from the moment A arrives in the ready queue to the moment it finishes and exits the system, it's 10 minutes because we're going to do A first. All right, now, how much time does it take job B to execute? Well, that's a little tricky. From the moment B arrives into the ready queue to the moment it leaves is 11 minutes. You might be saying, what? Wait a second, why is it 1 here and 11 here? Well, the answer is B has to wait for A to finish. So part of B's response time is the amount of time it takes for A to finish. You see? All right, so this is A, this is B. What about C? How much time does it take for C to finish? Well, you guessed it, I hope. It's 15 minutes because we have to add the time it takes for A and B to complete to the time it takes for C to complete. All right, how much time does it take for D? Well, that's A plus B plus C, 15 minutes plus D, which is, that's interesting. It should be 17 minutes. My note says 16 for some reason. I don't really understand why. That's a little weird. So yeah, it's 17. So if we add all these up, 10 plus 15 plus 17, and then we divide by the total number of jobs we'll get the average response time for a job. So I'm going to do that with my calculator here. Bring up the old calculator. And I'll just drag that in here so you can see it. So it was 10 plus 11 plus 15 plus 17 equals, and we're going to divide that by 4 equals. So we've got an average of 13 or so, 13.25 minutes is our response time. Now, what's our throughput? That's the total number of jobs that complete in, let's say, an hour. So it took 17 minutes to complete the 4 jobs. So if we take 60 minutes and divide it by 17, so we're talking about 60 minutes divided by 17 minutes for, that actually doesn't make any sense. Let's think about this for a second. So it took 17 minutes to complete 4 jobs. So if it took 17 minutes then if we take 60 over 17, that gives us 3.5. You're missing my, oh no, it's right there. Yeah, that gives us 3.5 times 4. That's going to give us the number of jobs. So about 14 jobs. Okay, so that's about 14 jobs per hour. That's our throughput. And our resource utilization is going to be, well, if we're talking about basically being CPU bound, well, we could use lots of resources when we're doing this. So the resource utilization we'll just say is some X. Okay, we don't really know. All right, so this is jobs arriving into the ready queue, but we're organizing the jobs first come, first serve. So let's look at another example where we change this around a little bit, okay? So what we're gonna change is, we're gonna do shortest job first. All right, so what we're gonna do is we're gonna take this, I'm gonna just copy that and bring it down here. So these are the jobs that arrive, but we're going to organize them differently. So we're going to do the shortest job first, which is job B. So job B is going to go first, and it's going to take a total of 1 minute for B to execute. Then we're going to do job D. So it's going to take job D a total of 3 minutes to execute. And then we're going to do job C. So job C is going to take, its response time is going to be B plus D, which is 4, plus C itself, which is 8. I'm sorry, yeah, B plus D, which is 4, plus 4 is 8. So that's C. And then D is going to take the time for C, which is, oh, I see. Oh, I see where I was making an error here. So sorry about that. So D is correct. D is 3. But then when we do C is actually going to be 7 because it takes 3 minutes to complete D and then 4 minutes to complete C. So that's 7. All right. And then A, it's going to take 7 minutes to complete up to C. So A is going to have to wait for 7 minutes, and then A is going to execute. So that's going to be 17. If I've got that done correctly. I think I do. All right. So let's look at this. So B, we added 1 to D's time. So that gives us 3. C, we're going to add 4 to D's time. That's going to give us 7. And then A, we're going to add 10 to that time. So if we add these up, 1 plus 3 plus 7 plus 17 and divide it by 4, we're going to get, oh, I see you didn't see me writing those down. Sorry about that. Calculator was in the way. Anyway, I hope it makes sense. So B takes 1. That's the first one to go. D takes 3. It takes B's time plus 2 minutes. C takes 7. It's going to take D's time, which is 3 plus the 4 minutes. And then A is 17. It's going to take C's time, which is 7, plus A's time, which is 17. Okay? So we divide that by 4, and we're going to get, let's see, 1 plus 3 plus 7 plus 17 equals, and then we're going to divide that by 4 equals 7. So we're going to have 7, whoops, sorry about that. We're going to have 7 minutes here. We can hide this calculator now. We're going to have 7 minutes as our average response time. So look at the difference here. We've got 7 minutes as our average response time with shortest job first, and we had 13¼ minutes, almost double that when we use first come, first serve. So although first come, first serve is simple because we're just putting it on a queue, here what we have to do is sort the jobs and then put them on a queue, basically. with that additional complexity, though, we get a much better response time. So it turns out that the throughput is going to be the same. The throughput time is going to be the same. Now, though, I want to go back and look at this and think about this for a second, because 15 and 17, yeah, that's right. Okay, so the throughput is going to be the same. It took 17 minutes to complete 4 jobs. And if we go to this example, our throughput is still going to take 17 minutes. It still takes 17 minutes to complete 4 jobs. And so we're going to end up with 14 jobs an hour. And our resource utilization is also going to just be X, the same. Both examples are going to use the same amount of resources over the period of time that we have over the 17 minutes. Okay, so I hope that makes sense. And the idea here is that you'll get a better average response time if you let the jobs that are smaller run first, if you give them priority. You're still going to get overall, the total time is going to be the same, but those processes B, D, and C that are smaller are going to get done faster. And so whoever's interested in those particular processes is going to be much happier. It's when you take this big process and have that run first and block the other processes that only need a little bit of time that you get into trouble. You're going to make those smaller processes unhappy. So we can kind of prove that shortest job first is awesome for response time. So let's consider that we have, consider 4 jobs. So that take A, B, C, and D. All right. So if you want to compute the response time, what you're going to have is A plus B plus A plus B plus C plus A plus B plus C plus D. That's you're going to take all that and you're going to divide it by 4. All right. So A is going to take, if we take A first, it's going to take A time if we do it first. B is going to take B's time, but also we have to add A's time to it if we're calculating the response time for B. C is going to take the time for A and B, as well as C. And then D is going to take the time for A, B, and C to complete plus D's time. All right, if we simplify that, what we end up observing is that we have 4A plus 3B plus 2C plus D over 4. So the influence of A, that first job that you choose, it has a big influence on the overall response time, the overall average response time. So you want to make sure this A is as small as possible, the B is next smallest, C is next smallest, and D can be the largest. What you wouldn't want is D to be in front and do 4D, because now you've really exploded the average response time for shortest job first. Okay, cool. All right, so the next thing I want to talk about is another type of scheduling algorithm, and this is called round robin. So this is typically used in an interactive system like a PC or Linux or a Linux box with the shell. All right, so generally you have many processes. They're that and they so you have many processes running and they want to share resources, including CPU, simultaneously. Okay, so that's the round robin scheme. And so the way the round robin works is like this. So you have a bunch of processes that are running P0, P1, P2, and we have some Pn. So these are all the processes that are running on the computer. And each process gets a period of time, Q, that it's allowed to run on the CPU. All right, so I'll just kind of, I'll just sort of write over here a couple of the rules. So a processes are preemptible. And what happens is process X runs on CPU for Q. That's the amount of time that it runs. And what we're going to do is we're going to context switch to px plus 1 if one of the following happens. All right, if px uses up q, or px exits, or px blocks, either for I/O or for synchronization. So that's the idea, and we're just continually running around and around and around. So every one of these processes gets a little bit of time to run if it needs it, and we change its state. So P0 is running, and let's say P0 is a big CPU hog, so P0 will run for up to Q time, and once that time has expired, we then pull P0 out of the running state and put it into the ready state, and we move to P2 or P1. P1's allowed to run, same thing. P1 runs and uses up Q, so we pull it out of the running state and put it into the ready state. Now we pull out P2. P2 starts running, and let's say P2 runs for a little bit, but does some I/O. So now we pull P2 from the running state and put it into the block state, and we then go to P3. And we just repeat this process over and over again. So the unique thing that we've added here is the ability to do context switching with this quantum. And we have a rule that it's round robin. So there is a queue, but the order of the queue doesn't really matter because we're going to just keep circulating around to each item that's in the queue and letting every process run for just a brief period of time. Okay, so we talked earlier about the one thing you have to watch out for when you do this is that you have to make sure that the quantum that you're using, so our goal here is we want to make sure that the quantum is big enough. Boy, only a spelling issue here. So you want to make sure that the quantum is big enough that the overhead for context switching is minimal. Okay, so I'll give you some examples just to reinforce this. Let's say our quantum is 4 milliseconds and our context switch overhead is 1 millisecond. Well, that kind of sucks, right? Because that means that the total overhead is for every 5 milliseconds, we have 1 millisecond of overhead, which means we have 20% overhead. So we have a sad face. All right, let's fix that. Why don't we set our quantum equal to 100 milliseconds, and our context switch time is still 1 millisecond. So that means we have 1 millisecond over 101 milliseconds, which is about 1% better. All right. So you just want to make sure that there's a good ratio between, a low ratio between quantum and context switching. In other words, the quantum's very large in comparison to the context switch. So Linux uses something like this scheme, this round robin scheme, and so does Windows, and so does OS 10. So, but there's a slight twist to it, which is, remember a little bit earlier, let's see if I can find it, go back through the notes for a second here. I said that that the scheduler's goal is to try to make sure that all processes have equal access to resources. But I said, well, maybe all processes shouldn't be treated equally. Maybe some processes are first class and others are second class. And so it turns out that in Linux we do something like that. Let me get down here. So I'll explain that. And it's a technique called priority scheduling. All right. And so the issue with round robin assumes all processes are equal, but we really don't want that to be the case. This is not practical. So, for example, maybe you have a multi-user system where you have a general, a colonel, a lieutenant, and a private. So maybe you want the general to have higher priority than a private. Or you have a system where you have an email client and a chat program and a music player. Well, maybe you want the music player to have a little bit higher priority than the email client or the chat program. So to solve this problem, what we're going to do is we're going to give, it's not practical because some processes need special treatment. If I want to speak about something concrete, the kernel process, the process that is the root or core of the Linux operating system, it's a process. Obviously, you want to give that a little bit higher priority than other processes that are running in the system. Okay, so how does it work? Well, what we do is we assign, the key here is we're going to assign each process a priority. All right, and we're going to use round robin for context switching, but with a priority queue, which means that when a process is done and has used up its quantum, or is doing some IO, so going to block state, or it's exited, the next process that's going to be executed is the process that has the highest priority. All right. So instead of just going around in a circle and treating them all equally, we're going to make sure that the next process we grab from the ready queue is the process that has the highest priority of the processes that are in the ready queue. All right, so how do we prevent CPU hogs though, right? Like if we only allow processes with the highest priority to run, it's possible that the processes that have the highest priority keep ending up bubbling up to the front of the queue, and processes in the back of the queue don't get that priority. And so the way to do that is that we're going to lower the priority. Okay, so let me just rephrase this. So how do we avoid starvation of lower processing? So how do we avoid CPU hogs or starving lower priority processes? So what we're going to do is the key to avoiding that is we're going to reduce priority each time the quantum expires. Okay, so this is the actual calculation that Linux makes to compute someone's priority. All right, so in Linux, this is how it actually works. So we have this priority value, and it's set equal to a couple of different things. All right, and I just want to tell you, I've got to follow my notes here, so I'm going to put a little note below this. So lowest goes next. The lowest priority goes next. So that's how we prioritize it. Okay, so it's equal to this thing called the threshold priority. And this is a value between 20 and 40. And I have no clue how this is set. Right, but it's some value between 20 and 40. We'll look at the things that you can mess around with, plus something called the nice value. And this is a value that you can set. So the default is 0, but you can set this 100. All right. If you say that, you're basically saying that this process is, let's see, let me just bring up a shell. Let's see if we can do it here. Okay, so you basically identify the process that you want it to, the process ID that you want to run nice on. And what it will do is it will add that nice value to the priority value of the process. So in the process of doing that, you're going to increase the, oops, it's getting kind of interesting here. I don't want to switch. So what you're going to do is you're going to increase the priority of the priority value of the process, which will lower it. It will lower its place in the priority queue, plus recent CPU usage divided by 2. So effectively, the time that you've spent running on the CPU. So this is going to go up as you use more and more of the CPU. This has a default of 0, but as a user, you can make it larger. You can't make it any smaller than 0. And like I said, this is some weird threshold value that I don't really understand how to set that. But anyway,